Hey everyone, this is Qian from UIUC. So last week in UIUC was our finals week, but somehow as I came to this conference, I started to feel the excitement and also the pressure of finals week again, because I'm looking at many familiar faces. I'm looking at my current collaborators and also potential collaborators, reminding me how many papers I need to finish after the conference. So in some way, this conference is not only intellectually inspirational, it's also shaping my plan for the summer. But for now, let me just enjoy our time to talk about the electron videography of nanoparticles in my group. So I'd like to first motivate with this idea of why we care about direct imaging using this art question. So you will all know the great artist Van Gogh, and some of us know once he was very happy with his new bedroom in Valhalla. So what are the ways for him to describe his new bedroom? One way to do that is to use words to detail the shape and position of everything, like what he did in his letter to his little brother. But the other way was to paint it, like showing here. In comparison to words, a painting has direct spatial information, and there can be many different ways you can interpret the interplay between light, color, and shadow. So Van Gogh's time did not have computers, but more than 100 years later, with advanced computation power, people are able to revisit this painting to do quantitative analysis on the brush stroke and painting style. So this is the time-enduring beauty if you have one single image. And what I'm going to talk about today is we want to go beyond even just one single image to actually take movies using electron microscopy. So in the field of electron microscopy, the common practice you deal with an electron microscope is that you will use a dry sample and put it into a microscope, get a two-dimensional projection view of the sample. In a lot of applications, this is good enough for you to know what is the size, shape, distribution of your sample. But what we are able to do, thanks to the recent advancement of electron microscopy, is that there are three different ways we can actually take electron videography or take movies using electron microscope. So the first way is the method of liquid phase TEM, which allows you to put a liquid sample against a high vacuum electron microscope. So by doing so, not only you can see the final structure of a sample, you can also see the vivid, thermally agitated dynamics of the sample. And the second way is instead of just having one single two-dimensional projection of the sample, you can piece together a series of two-dimensional projections of the same sample, different orientations, from which you can reconstruct the three-dimensional conformation of the sample at sub-nano voxel resolution. And the third method is going beyond real space imaging. You can focus your electron beam into a nanometer-sized probe. And this nanometer-sized probe can interact with your sample that is nanometer by nanometer in area, and then generate one electron diffraction pattern. And then you can raster scan this electron beam to collect a series of electron diffraction patterns. So this is a very powerful way for you to receive the shape, the crystalline phase, the phase orientation, and also the strain distribution within this single nanoparticle at a nanometer resolution. So with those new methods of electron videography, we can actually get new insights on various different types of systems, in particular on understanding of the formation, the control, the function implication of shape and dynamics at the nanometer nanoscale. So in particular, for example, we can take movies of phase transitions. We can also take movies of biomolecular dynamics. So this for a long time is only possible for molecular dynamics simulation. But now we can do so in real space and real time in experiments. We can also take movies of polymer morphing. We can also take movies of electrochemical reactions, which is very important for energy storage applications. So I'm going to talk a few systems with an emphasis on how electron videography can actually give us new insights. So the first type of system, or the first type of system we're going to focus on is nanoparticle self-assembly pathways. And the major tool we're going to use is liquid phase TEM. So here I'm showing 3 photos of my students. So sampling the different aspects of daily practice if you are involved in this project. So for example, we have people like Johnny who is sitting in front of a computer dealing with the huge data set that is coming out of electron videography. Many different aspects, machine learning is very important. And then we also will have students like Zihao who will sit in front of the electron microscope, enjoying his time capturing movies in situ, actually doing some in situ control of the solution during the self-assembly process. We will also have students like Chang showing here, who will spend hours and hours time in front of the electron microscope, utilizing the most current beam technology to make sure we get what we want to get. So with those pictures in mind, the result or the outcome of the studies is that we can actually understand a series of different phenomena. So now I'm going to walk you through on the different scientific questions we can study. So the big focus here is to really understand the emergence of order from nanoparticle building blocks. So when it comes to nanoparticle building blocks, whether it's synthetic or natural, you can always have them form into a crystal. And the crystal property can really be sensitively dependent on the arrangement of the nanoparticles. But for a really long time, people don't really know how those nanoparticles can actually form into the superlattice, usually out of a very, very well-dispersed suspension phase, undergoing random Brownian motion, and how they actually form into a crystal in the end. So at the same time, if it comes to the modeling of these nanoparticle interactions, that's actually also not simple because they can have non-additivity. They can also have multi-scale coupling effects. So that's actually how our usage of liquid phase TEM can actually fill the gap. So using liquid phase TEM, you can literally take in real space and real time nanoparticle self-assembly movies. So you can really watch how individual nanoparticles interact with each other to form into the final superlattice structure. I'd like to mention right now there are two ways to do liquid phase TEM. One way is to use this microfabricated chamber, which can allow you to put a liquid sample in against the high vacuum electron microscope. At the same time, you can actually change the conditions. You can change the temperature. You can do solvent exchange. You can also apply electron bias during the imaging. And then at the same time, you can also use this graphene sandwich, which is very similar in principle, but it can give you even better spatial resolution and higher contrast, which is wonderful if you want to study polymer or protein samples. But before we run into using this technique for studying self-assembly, let's just be careful. So this is a beautiful work done by Qian Chen, who will be talking after me. So he shows by manipulating electron beam during such liquid phase TEM imaging, you can actually literally induce this beam-induced nanoparticle reactions. So for self-assembly experiments, that's why for quite some time, we're trying to really make sure we do a lot of correlative or control experiments to really make sure during our experimental observation, the electron beam is not going to introduce reactions to the nanoparticles. As a result, you are really seeing the generic dynamics of nanoparticles. So with these basic protocols established, now let's actually see step by step how we can understand the crystallization dynamics of nanoparticle building blocks. So the first step of crystallization is nucleation. So when it comes to nucleation, which is essentially the first emergence of ordering, you can have classical nucleation, and there's this more modern terminology of non-classical nucleation, which is summarized in this beautiful review paper here. So when it comes to non-classical nucleation, it means instead of having individual building blocks directly forming to the final crystal, it will actually undergo a diversity of pre-nucleation motifs. So these pre-nucleation motifs has been shown in atomic, molecular, biomolecular, or ionic crystals. So our question is, how about when the building blocks are actually inorganic nanoparticles? So this motivates us to do this first set of experiments where we have a suspension of individual nanoparticles put into our liquid phase TEM chamber, and then we induce this crystallization process by increasing the interparticle attraction. And this is what we can see. So in this movie, the black particles, the black things are actually our particles. So you can see, you can really tell from the very beginning, a very disordered suspension can interact with each other, and that's actually how you can get a final lattice showing here. So this was the first time we're able to capture this process in experiments in real space and real time. And then what is the usage of this? Yes, in solution. Yes, when solvent stays there, that's the magic of the technique. Yes. So what kind of quantitative information can we get out of the movies? So this is a work done by the student's house. So what he is able to do is to do single particle tracking. So showing this liquid phase TM movie, now each black feature is overlaid with a green dot, highlighting the central position of this particle. And then at the same time, based on the single particle tracking, you can do this binary cell analysis. So based on this binary cell analysis, which is highlighting the bond connection network of the structure, you can now start to calculate 2 local order parameters for each particle. So one order parameter is the local bound orientational order parameter, which is highlighting how locally ordered the structure is. The other is local density, which is characterizing how concentrated this particle is. Because we have a lot of particles, we have a long movie. That's how we can get this 2-dimensional probability map. So out of this map, you can clearly see there are 2 states in the system. So beyond this one state corresponding to high structural order and high local density, which is our final crystal, we also have another state that is of low structural order and high local density. And that's our pre-nucleation motif. So we can do this for the whole movie. And in this movie of this 2-dimensional map, you can see indeed at the early stage of nucleation, you mostly are sampling this pre-nucleation motif. And towards the later stage of the nucleation, that's when you start to have more and more sampling of this crystalline state. So this is all obtained from experimental data. So after this, we can go back to label our particles with different colors. We have the yellow particles at the very beginning. We have the final red crystallize. We also have the extensive blue region, which corresponds to this dense amorphous pre-nucleation motif. So in our later work, we show this presence of this dense amorphous pre-nucleation motif can actually lower the energy barrier for nucleation. I'd like to re-highlight around the same time, independently, Sharon published this beautiful paper with different nanoparticle shape and size, they can also see the presence of pre-nucleation motifs when it comes to crystallization. So since this is a quite universal trick when you are using nanoparticles as a building block. So this is our understanding about the nucleation process. And the second step of crystallization is the so-called post-nucleation growth habits, which is actually also terminology that is inspired by atomic crystallization. So the inspiration is partially from this work showing here, led by Yunan Shah at Georgia Tech. So you can see in this example, even if you start from a seed particle or nucleation site with a very well-defined symmetry, given different growth conditions, in the end, the atomic crystal can adopt very different shape. And similarly, we know the nanoparticle building blocks, they can also form into superlattices of different shapes. So we want to understand what is the growth habits that can really determine the size, shape, surface morphology of a superlattice. And that's not a simple question to understand because to study that, you need a much larger system. At least you need to accommodate enough particles so that they're actually going beyond nucleation. And second, as I'll show you later, this question concerns multi-scale dynamics. So not only you need to consider interparticle interaction, mass transport start to also play a very important role. So that's how we started to take this challenge experimentally. So my former student, Bingbing, he was able to substantially upgrade our protocols for liquid phase TM imaging so that now we can accommodate a much larger crystal in our system. And he was also able to synthesize a series of nanoparticles of different shapes. So let's look at their behaviors one by one. So in the first example, this concave nanocubes, if you look at the movie, you can see the growth front will always finish one layer before another layer. So this is a so-called layer by layer growth. It ensures the surface is a very smooth surface. It does not have random protrusions. And then if you go to the other two types of particles, although the shape and symmetry are very different, they also follow the same layer by layer growth. So as you mentioned, the layer by layer growth is actually very commonly adopted by atomic building blocks. That's actually how you can get atomically flat semiconductor films for device application. So since layer by layer growth is actually a very simple and easily to achieve growth habit, but very quickly we realized that's not really the case. If our nanoparticles are much bigger, say now become micrometer in size, so here on the movie on the left, which is an optical microscopy movie with a scale bar of 10 micrometer, you can see now the crystal surface become really rough. So this first hint of building block size dependence inspires us to think about what is the reason. So one simple reason here we can think about is there are two important diffusion processes when it comes to crystal growth. So where one is in-plane diffusion, the other is interplane diffusion. So for either diffusion modes, nanoparticles can actually diffuse orders of magnitude faster. So that can actually explain why nanoparticles are easier to have layer by layer growth. But at the same time, is the layer by layer growth the only growth habit they can have? That's actually the beauty of doing experiments. So in experiments, the experimental results can actually sometimes surprise us, going beyond our theoretical understanding. So here I'm talking about the big crystal. So if you think about big crystal in 3 dimensions, minimally you can have 2 growth directions, the in-plane growth direction and out-of-plane growth direction. For each growth direction, they have a choice of having very smooth boundary or rough boundary. So in total, you should expect there are 4 growth modes. And indeed, in our liquid phase TM imaging of nanoparticles, we can also see the 2 additional mixed growth modes. So here in those 2 liquid phase TM movies, the particles are the same color, meaning the particles are actually in the same layer. So for the top movie, you can see the 3rd layer started to grow even before the 2nd layer finishes. That means outer plane is not really layer by layer, it's corrugated. But within each plane, you can see the boundary of the layer is very smooth. So in plane is layer by layer or row by row. On the contrary, if you look at the movie below, the 2nd layer will start to only grow when the 1st layer is completely finished. So this outer plane is layer by layer, but if you look at the shape of each layer, it's very rough. So this is another example of mixed growth modes. So those 2 mixed growth modes haven't really caught a lot of attention before our study, and that's actually how we were motivated to talk with our collaborator, Eric Lawton, and his former student Ziwei, to understand what really determines the 4 growth modes. So they were able to do a lot of kinetic multicolor simulation over a large parameter space. So there are 2 pieces of information I'd like to highlight. So first of all, they're able to use simulations to reproduce all the 4 growth modes as shown in here. And second, because they're able to do a lot of simulations, they can plot out this phase diagram. In this phase diagram, the x-axis is the ratio of the energy barriers. The y-axis is diffusivity over flux. And actually highlight in this phase diagram, somehow the different sized building blocks, they can just sit in different regions of the phase diagram. So for example, for atoms, they tend to sit in the square region, which corresponds to layer by layer growth in both growth directions. So that's why atomic crystals tend to adopt faceted shape. And then for the micron-sized colloids, they tend to occupy this circle region, which corresponds to correlated growth in both directions. And that's actually very consistent with a large body of literature on colloidal crystallization. And the beauty is with our nanoparticles here, it can actually sample all the 4 different growth habits, which agrees with our experimental observation, which is also the reason we can have a huge flexibility in terms of the bulk defect density and also the final crystal morphology if you are using a nanoparticle building block. So this is our understanding on the growth modes or growth habits of a nanoparticle superlattice. So if you are curious why we care about this very fundamental understanding, I'd like to just show you quickly with one example here. So this work is led by my former postdoc Shan, who is now a faculty. He introduced to our group the capability to synthesize gold tetrahedral nanoparticles. Using those gold tetrahedral nanoparticles, my PhD student Jia Hui was able to disperse those gold tetrahedral nanoparticles in water and then look at their self-assembly in liquid phase TEM. And this is a movie she was able to get. So in this movie, there are also 2 features to highlight. One is the tetrahedral nanoparticles actually form into a very ordered structure. And the second is you can actually see there are a lot of voids in this ordered structure. So to put it in context, tetrahedron is actually a very popular shape in terms of a building block. So in this pioneering work by Michael and also Sharon, they show the packing that is possible with tetrahedron, including some very fancy structures such as quartz crystal, which are different from what we saw here. So it took us quite some time to understand the formation mechanism of our structure here. In the end, we realized it's because we do have a substrate, and the substrate can actually serve as a template during the self-assembly. So because of the presence of the substrate, the tetrahedron needs to have one facet to recede flat on the substrate, like shown in this orange particle here. And then at the same time, we'll have another layer of tetrahedron that is pointing downwards to fill in the void space. So that's why we're able to utilize this mechanism to essentially retrieve the same structure outside liquid phase TEM chamber, but now in the dry state on a silicon wafer. So this is what you see here. So this is what we get outside TEM. And then Alex was able to help us to look into the structure to show this is indeed a structure with a lot of voids. In fact, the packing density is as low as 1/3. And then our other collaborator, Kai, was able to show this open lattice, this porous structure is actually a very interesting Maxwell lattice. It can have interesting deformation modes. In fact, we're able to utilize one of the deformation modes shown in this animation here to collapse what you just saw into a chiral symmetry breaking lattice as shown here. So if you look at this SEM image of the superlattices, now the triangles, they're all twisted against each other. And the twisting is actually happening because we're effectively compressing this lattice to decrease the void space. And then later, in collaboration with Li Kotov, his postdoc Jun Lu, and together with Dr. Hanhua Liu at Argonne National Lab, were able to pinpoint this chiral lattice actually has chiral optical property as confirmed by both simulation and also ultra-fast electron microscopy imaging. In terms of what is ongoing, so there are different ways for you to rethink about nanoparticle dynamics. One way to review them is actually from the lattice dynamic theory, where you can see the local vibration of a nanoparticle in a superlattice as part of the phonon response. So in collaboration with Professor Wen Xiaopang at Wisconsin Madison and Xiaoming at Michigan, we're able to map out what is the phonon vibrational modes of the superlattice at nanometer resolution. So Xiaoming will talk more about this work tomorrow. And at the same time, going beyond from equilibrium self-assembly, we can also push for non-equilibrium self-assembly. So this is work done by my student Chang. And in this case, we're able to apply electric field to the system. So now you can see the particles become a lot more vivid. They are really actively agitated. We did some calculation to show electroosmosis flow is the key drive here for the motion. And also see this experiment as really the start for us to understand and engineer active matter at the nanoscale. And then I talk a lot about liquid phase TEM. I want to tell you, at the same time, we also have a decent component of white chemistry lab in our group. So showing here, my former student, Ayang, she was looking very proudly of the nanoparticle suspension she was able to make. And then for those particles that are of very complicated shape and geometry, so that's when electron tomography becomes very important, which is the expertise of Fallon, who is also looking at the chemical bottle right there. So the reason why we care about patchy nanoparticles that Ayang was synthesizing is because this is actually a perfect way to emulate the complexity of biomolecules. So showing here, for both virus and proteins, they can have very rich patchlets on the surface. In the materials design principle, a patchy nanoparticle can facilitate delivery across the cellular membrane. They can also serve as self-propelling nanomotors. They can also self-assemble into these open lattices, which can have very interesting optical and mechanical properties. So that's why we care about them. But the challenge here is how to actually have patchy nanoparticles with very uniform patch formation in terms of the position, the size, and the shape of the patch at the nanometer precision. This is a very important question, so that's why there are a lot of pioneering work. even if we're just limiting our discussion to patches that are made out of polymers, there are already different strategies. For example, you can actually have polymers homogeneously coating our particle surface and then introduce a change to induce the polymer-polymer patch segregation. You can also use selective ligand exchange with starting from 2 ligand mixtures, which will later spontaneously self-separate in order to form into patchy particles. So that's why I was pretty happy. Then one day, Ayang came to me with another strategy. So Ayang didn't show me anything related with nanoparticles. Instead, she showed me a movie of bacteria. So in this optical microscopy movie here, with bacteria, you can actually control the spatial distribution of the bacterial colony and then control the growth dynamics. That's actually how you can get this really rich pattern library showing on the right. So Ayang's idea was, how about we actually control such nucleation and growth, but not on bacteria, but on ligand molecules on top of nanoparticles. So that's what she was able to do. So in this example of triangular nanoprisms, she incubated triangular nanoprisms with thiol ligands that is hydrophobic, and then a block of polymer with polystyrene and polyacrylic acid. So by doing so, the thiol ligands will selectively attach to the end or the tips of the triangular prism, and then the block of polymer will absorb onto the tips due to the hydrophobic attraction. So this turns out to be a very efficient strategy. We have a high yield of this tip-coated triangular nanoprisms. And also we can further control the size of the patch by increasing the ligand concentration. Showing these AFM images, the patch size will start to laterally expand until they start to merge with each other. So those are the 2 lobes we're already talking about. And then the third lob, which turns out to be very interesting, is polymer-polymer attraction. So polymer-polymer attraction is actually a very easy to control handle here because the chi parameter in polymer physics just need to be changed by changing temperature. So that's what Ayang did. She did the identical experiment, but now doing the experiment at a lower temperature, which increases the polymer-polymer attraction. And then this is a surprise she saw. So instead of the tri-tip coated triangular nanoprisms, now you only have 1 tip that is coated with a polymer patch. So in other words, we have a symmetry breaking effect. We're able to use electron tomography to verify indeed this is a particle we got. The hypothesis we have here is that when the polymers are very attracted to each other, they tend to segregate as closely as possible. So that's why they will have 1 tip. Well, when the attraction between the polymers are weaker or even repulsive, that's when they would prefer to evenly distribute over all possible sites. So in some words, this is like a bandwagon effect. The polymers which are stochastically first absorbing onto 1 polymer tip can serve as a recruiter to keep attracting more and more polymers onto the same tip, just like how people will try to conform to other people's opinions. And this picture was captured by Sharon and also Sharon's former postdoc T, now faculty here at Johns Hopkins. So in T's simulation, he was able to show in real time the polymer absorption dynamics. So basically, at very strong polymer-polymer attraction, the polymers would prefer to keep adding onto the same tip. I also want to re-highlight T's modeling is really quantitatively powerful because not only the model can predict the patch pattern, it can also predict the patch shape. It can really predict why we sometimes have this pendant-like patch shape, why sometimes we have a more flattened patch shape. And this patch shape is very important because ultimately we're able to introduce patch-only attractions in the system to introduce interesting sub-assembly as shown on the right. And in terms of what is ongoing right now, we revisited the first lob in our patchy nanoparticle synthesis, which is how to control local curvature of the nanoparticles to determine where do the patches absorb onto. So this is when we go back to actually look at a huge nanoparticle shape library as shown here. And this can really show us the capability of the method. So now with a much larger library of patchy nanoparticles, our future outlook about this is how about we incorporate more nanoparticles in the liquid phase TM study to look at how they self-assemble and how they interact with each other, how they can form into open structures, and how to actually use them as self-propelled nanomotors. So with that, I'd like to come to really summarize on how we see the power of electron videography. I'll give you a few examples. I want to highlight with the recent advancement of electron microscopy, there's really unlimited possibilities out there. We summarize our thinking and also current literature in this chemical reviews paper we just published. So in this chemical reviews paper, we highlighted the experimental challenges, the data science, how to do in situ imaging, how to prepare your sample, how to analyze your data using machine learning. So all in that one paper. We hope this paper can actually become a handbook for you if you want to deal with electron microscopy and the more modern nanomaterials. I also want to mention in the talk today, I haven't talked about how we can actually use the biomolecular conformations to understand the mechanical properties of proteins. I also didn't talk about how we can use electron tomography to actually to understand the morphogenesis of polymers during synthesis and also transformation. I didn't talk at all about machine learning, but that's actually behind every single plot I've shown you. I also didn't talk about energy storage materials. That's probably about another 30 minutes talk. So with that, I'd like to thank you for your attention, thank my group, thank all the funders, because electron microscopy experiments are really expensive. Thank you for your attention. We'll be happy to take any questions you have.
Thank you very much. Wonderful talk. In the early pictures of these gold superlattices, it looked to me like there is a little bit of like connection between particles. Was I imagining this, or is there some connection forming?
I see. So you're talking about the movies of the nucleation process, right?
I guess it was in the early slides in 10 or something. It looked like there is some bridge, small bridge, very small. I don't know if it's real.
Yeah, that's a great point. So there is an interplay between the nanoparticle diffusional dynamics versus our temporal resolution. So right now, the temporal resolution of movie taking is the best is about millisecond. So you can imagine if the particles are diffusing faster than that, then you're going to, for each image you're basically taking kind of a blurry image. That's why you can have those connections, but those are not really real physical connections. And the reason why this is so good for self-assembly studies is because once the particles are self-assembled, the diffusion is significantly lowered. That's actually how we can see single particles really clearly after they are assembled.
Any questions online too? Feel free to raise your hand if you're online and we can ask your question.
It's a beautiful talk. Thank you for that. I have a question about the layer by layer growth part. So typically, at least in atomic systems, the transition between layer by layer growth or continuous growth is a roughening transition, which also in the non-growth conditions results in a faceting transition of the collection of particles. So I wonder if you've been able to correlate the transition between layer and layer by layer growth and continuous growth to the overall morphology of the particle.
Right. That's actually a great point. So usually when people talk about the roughening transition, it's actually more of a thermodynamic effect. So the driving force for that is basically when you're at a higher temperature, you will prefer higher entropy, and then having a very rough surface is one way to get higher entropy. So in our case, that's exactly why here is the growth habits. So it's more like a kinetic effect. So in other words, for all the 4 growth modes I'm talking about, if you think about the system thermodynamically, they will actually prefer very smooth surface. So it's really because kinetically, in order to achieve a smooth surface, you need to have the building blocks to move very quickly. Sometimes that's not always a requirement that you can satisfy. Also, sometimes that motion of the nanoparticles, you also need to be put into the context of flux of the particles. So that's why we have those parameters as the coordinates of the growth modes for the phase diagram.
Thank you.
Beautiful talk, thank you. I had a few questions actually on the liquid TEM that you use. I was wondering about the typical thickness of the samples and whether it must be aqueous or perhaps also non-aqueous, and also perhaps if you can apply other gradients than electric fields, for instance, temperature gradients or other driving forces.
Right. So in terms of thickness, that actually depends on what you want. So for example, if you're dealing with a polymer or protein sample, because the generic contrast is already very low, for those kind of imaging, you want to make sure the liquid is pretty thin. Otherwise, you contribute a lot of background noise. So for those cases, we will use the graphene liquid pockets, and that can actually give you about tens of nanometer to hundreds of nanometer liquid thickness. And then for our self-assembly experiment, that's very different, because for our self-assembly experiments, as I mentioned, we need to have large enough free space for a lot of nanoparticles to diffuse and interact with each other. So for those experiments, usually the liquid thickness needs to be several hundreds of nanometers or even larger. So the balance you want to have is if the liquid thickness is too large, then the resolution is going to be lower. So that's just something one needs to keep in mind. And then in terms of the solvent, both organic and aqueous solutions can be used, but the holder usually is actually made out of a certain metal part, so there is a compatibility you need to try to do. So for example, if you're dealing with very basic solution, usually it's not compatible, so that's just something to keep in mind. And then going back to the kind of stimulus you can have, so I show we can have electrical biasing. At the same time, you can actually heat up the sample. So actually heating up right now, the way people do that is the same as electrical biasing. So you can use dual heating to actually change the temperature of the liquid. And you can also do liquid exchange by liquid flow. So the reason, basically for all of our equilibrium self-assembly experiments, the way we induce this crystallization process is by increasing the salt concentration of the system, and that's actually achieved by liquid flow.
Impressive. And if I may, could you make the channel tapered?
Tapered. So by tapered channel, you mean you have different thickness of the liquid?
Yeah, or a large inlet and a narrow outlet.
Yeah. That's actually completely engineerable. So this microfabricated chamber is really utilizing microfabrication to design the chamber. So basically, the only limitation is how one can actually do lithography on those chips.
Splendid. Thank you.
Hi. So in your faceting studies, I'm curious, if you were actually growing a nanoparticle, you would have bonding, and there would be surface energies that would basically, help define your faceting, right? And so I'm curious how you think that bonding would affect the development of your layer by layer versus, continuous growth. Would that affect your regimes at all, or would you just get the same thing?
Right. That's actually a wonderful question. We have a work that I didn't cover here that is really just talking about the facet-dependent surface energy. So when people do this morphology controlled nanoparticle synthesis, the general principle is that the surface energy for different facets of a atomic crystal is different. So that's why the absorption and also sometimes the growth kinetics is anisotropic. So we can actually have something very similar for nanoparticle superlattices too. So we have another work where we actually measured what is the surface stiffness term for different faceted supercrystals. And indeed, there's a facet dependence. So if we put it into the picture growth habits, again, that's more like a thermodynamic argument about surface energy, while here is more about kinetic growth modes. So they are related to each other.
I'll take this chance to ask a question then. Chen, so you were showing there was some field-directed assembly motivation, right? So I imagine if you're placing a particle in a field, it's going to get, there's going to be a dipole that also push it along
prefer orientation as well, right? Have you looked into things like that as well for your particle assembly?
Yeah, we haven't done that. So right now for that experiment, we're using spherical particles. That's why we're thinking in the future we can either use anisotropically shaped particles like a rod, or we can also use those patchy nanoparticles. So for example, if we just have one patch on one end, that would introduce a generic different symmetry out there. That could be interesting. Another thing we also haven't tried is when it comes to electric field self-assembly, there's actually a huge parameter space in terms of the frequency and also the field strength. So we didn't try that thoroughly yet. So that's why I feel that's like the starting point of a lot of possible experiments in the future, right?
Yeah, also really beautiful talk. I have a question concerning the movies you showed of the growing superlattice. And now some of the superlattices we get from simulation, but also from experiment, are really complicated. I mean, those that you showed were relatively simple. You just have layer by layer. But we also know, at least from our simulation, we know that there has to be a lot of trial and error in these assembly process. So it's not just, the particle cannot just come and dock and then stay there. Is there a certain by a certain selection bias because you probably choose systems where the particles stick pretty strongly? So is there any hope now, or maybe also in the future, to look at these more violent systems? Violent, I mean, it's more dynamic and it takes a longer time to really settle in. I mean, right now it's probably very difficult, but in future, is there any hope to get also to these systems?
Right. So first of all, most of the movies are real time. The self-assembly is really quick because those are nanoparticles. They diffuse very quickly. But there's actually no real limit in terms of observation window. So for example, if the self-assembly takes hours to complete, there's no problem at all. And the second, when it comes to how they can relax into order, I think the ultimate question is how to really escape kinetic traps in the system. So that's always a challenge out there. If the system becomes more complicated, the free energy landscape will become more complicated. In those cases, one possibility would be to utilize these in situ modules to actually do some annealing of the process. For example, we can actually heat it up a little bit. That might be helpful. And right now, the heating temperature range is from room temperature to 200 degrees C. So it's actually pretty powerful.
Any other questions?
You've shown in the beginning of the talk of this self-assembly of, as I understand, triangular particles, right? So you were focusing on two order parameters.
Yes.
One is bond orientation, other parameter, another is just local density.
Right.
Is it feasible to actually measure the orientational order parameter associated with particle rotation itself? Because this is different, right? So
I see.
Is it practical?
Yeah, that's definitely practical. That's a great point. So I should mention in all those movies, the spatial resolution is nanometers. So in that particular example, although it's triangular prisms, it kind of stack up. So in the end, you get a circular shape. But if you're dealing with a cube, for example, you can see the contour very well for a cube. We can actually check the orientation. So we can get how orientationally, if that order or not, without any problem.
That would be cool because it's an additional order of parameter.
Yeah, exactly.
Non-trivial interplay between them.
Yeah, exactly. Yeah.
I mean, so you got this, sorry, it took a little while to turn on. So you've got this liquid cell TEM that's, how thick is it normally?
Normally it's a few hundreds of nanometer.
And your particles are much smaller. So I was just curious how you're tracking the growth, especially if it's 2D growth in that 3D space.
Right. So here, I skipped some details. So that first of all, the crystals we find they are not really confined to 2 dimension. They do grow in 3 dimension, and then as they grow in 3 dimension, depending on how thick the sample is, sometimes we really just see the individual particles all overlaid with each other. But then in this case, for example, in those movies I'm showing, oops. Okay, now it's not really showing. So in the, right there. So in those movies I'm showing, this is a three-dimensional growth. We have multiple layers of particles. So here we're utilizing the beautiful property that with different thickness, you will have different intensity of the signal. So that's how we're able to tell, oh, this is the first layer, and those orangish color is actually the second layer, and then this yellowish color is the third layer. So we can still get decent tracking there. And then I also didn't talk about another of our recent work on a complicated three-dimensional lattice. So in that case, we can also use machine learning to allow for single particle tracking.
Yeah, I was thinking mostly about the first one that you showed us with the triangular prisms. Is that two-dimensional growth? And is it occurring on a surface?
Three-dimensional.
It's three-dimensional
yes,
as well.
Yes.
Okay. All right, thank you.
So in the interest of time, we can follow up with Qian with a question during the break.
Yeah,
and,
I'll be here for the whole week.